First of all, inviting me here. It's yeah. I'm glad that you found some of these things to be relevant, and I'm very happy to see, later on what kind of stuff you are working on. And that's a quite new work, and so we didn't even get the reviews yet, right? And yeah, so this is why that will be a preliminary kind of presentation. But I think so, hopefully I can convey some of the messages that we want to convey in the paper. Yeah, topic is going to be on neural operators, but with a topological twist. Okay. So this is the problem, right? We want to solve PDEs, and these PDEs are usually defined as some kind of functions in certain literature, right? They call this drift and so on. And these are defined, given time, and some function u. It's a function of the gradients and well, Hessian and all the rest of the derivatives. And then you are trying to record basically the evolution of this function, starting from some initial conditions, some boundary conditions, and so on. And you assume, well, I assume in the rest of this talk that there will be a solution operator, right? So that at some point in time, this solution can actually be given by some kind of a operator or a function that is going to given enough information, it's going to be outputting me the solution at time t, or t plus tau in this case. Okay. And for the rest of this paper, I mean, you see that there is time is here, a property, and it's actually very important that you are able to query this in given arbitrary times, right? And that is something I'm going to ignore, and I'm going to talk about the steady state of this. So given some boundary conditions and initial conditions, we are going to always predict what would happen at the steady state. Well, some PDEs don't have a very nice steady state, as you know. And so the assumption is going to be that there is a steady state that I can obtain. That's not always easy, because depending on the parameters of the PDEs, some PDEs sometimes have steady states and sometimes not. Right? So that is delicate, but that's a problem I am prolonging to a later stage, essentially. Okay. So there is this paradigm in neural operators, which is very nice, because now what you are asking is not just a map, right, between some input x point and an output point y, such as x to x squared, right? But you in fact want to map given some function to another function, right? And then you can, for example, write this map to be this kind of an integration, which is a function. And of course, you also want to think about this operator view, where you go from one function to another function, and there exists this operator which you can operate, right? For example, you can take the gradient. The gradient is an operator in the maths language, right? And then you can apply the gradient operator onto this function f to get the gradient of f, which is another function, right? So you could either think of mapping in the space of functions, right? But you could also think that there is an operator which, you could apply to different functions to get different output functions, right? Which is nice, because it's essentially saying that, if you can learn such an operator, right? Or if you can think of obtain such an operator one way or the other, that means you could learn, or you have the ability to solve that PD, right? Regardless of what function is given to you. So that's kind of the premise. And you could think of this as the input as your, initial conditions and boundary conditions presented to you as certain functions. Right? And then you want to learn a solution field, which is an output function. And in between, you have your PD solution, okay? Whatever that might be. So examples of this is, right, heat. You start from some initial condition and you solve the heat equation, and you get a temperature field parameterized by T, right? And if you take T to infinity, right, steady state, you would be obtaining some, or large enough T, let's say, you would be obtaining some steady state solution. Alternatively, you can think of this source currents are given, and then you solve the Maxwell's equations to get the electric field, right? Again, the same paradigm exists here. So, people have been thinking about this for a long time, of course, and I'm by no means a physicist, so I have little experience in this. But what happens in general is that there is this repeated regression problem where you are presented your initial conditions and boundary conditions, coefficients, and then you are also given, let's say, as a result of simulation, some output functions. Okay? Now you want to learn the map, or you want to learn to map the input function to the output space, the output function. And of course, you can gather this as training data and train a giant neural network to realize this for you. That's the classical paradigm. So neural operators started with this idea, of ambitious idea of solving PDEs just like that. And in doing so, on a large enough data and learning in the function space, they might actually learn the operator that might solve the PDE and not just do regression as is. I think along the way, this paradigm has changed a little bit, and people typically use neural networks, or at least a part of the literature would just use neural networks without thinking about functions and try to learn the input space to the output space. That is now thought to be a valid neural operator, actually. Okay, anyway, there are many architectures that can realize this. So for example, Fourier neural operators is one. You take your input, okay, field, and then you take a Fourier transform and then operate in the Fourier space. And this, of course, doing this in Fourier space is nice because you can have these interpretable kind of layers in between and so on. And then you can assemble these Fourier layers one after the other. This is just basically designing a neural network in the frequency domain. Okay, so you can do that, of course. But in the end, what you are doing is you are trying to map input functions to output functions by designing certain architectures. Right. So this would be, for example, starting. So this is a vorticity PDE, and starting from some initial condition, you evolve. So by the way, shall I take questions as we go?
Yes, Prof, but it wasn't a question, it was
Okay.
a general note.
Yeah, so whenever you want to ask something, maybe shout, or in the end, we can also discuss, but you could also shout. I don't mind.
Sure.
So you start from some initial guess, and then you just iterate this. This is the upper row here is the solution of the PDE, okay? And then you train your Fourier neural operators, and then you get certain predictions at given times. So again, this is valid for this is a time conditional thing. So you can actually query the solution of the PDE at arbitrary time points. Well, okay, realizing that this is just designing neural network architectures, people went ahead and kind of developed these transformer-like, state-of-the-art machine learning pipelines as neural operators. Okay, and of course, this involved, for example, in the case of transformers, tokenization. So they propose this physics-aware tokenization, right, and adapting any transformer architecture to this domain. Okay. Here, of course, we work with a discretized domain, right? But people try to do, as much as possible. They want to go away from this, discrete voxel spaces, but it's not always easy. Anyhow, once this is done, then they replace the standard attention with some kind of a physics-aware attention. Okay, I'm not going to go into the details because this is not my work also. But yeah, essentially this slicing and then tokenization and deslicing is the idea here. And this has been the state of the art also for a good while, I would say. right? And it operated on these, 3D and 2D structures, okay, and gave good solutions to PDs. So one way to look into this PD solving is as follows. So we can take our PD. So here there is my linear operator, okay, and then there's the f, I guess, and some initial conditions. And then you can define some green function, which is, I'm not going to go into the details, but this is defined as the unique solution of this LG equals delta x, where delta x is a direct measure at x. Okay, and then the operator, the ux, can actually be written as an integral form, where you have the green function in front of f. Okay. So recognizing this form and the structure of the green function, people notice that they can actually write this integral as a kernel. So as a kernelized form or as a kernel form. Okay, so we have some kind of a kernel function x, y, a, x, a, y, and f remains as is. Okay, so this is of course the continuous kernelized version. But once you discretize this kernel and you recognize that this integration is essentially message passing. So kernel integration is essentially message passing plus an aggregation, right? So they truncate it over some neighborhoods and sum up these contributions and think of this as a neural network layer somehow, okay? And then there are these W's, and then there is the neighborhood that do take edge features and then output some kind of a matrix. Right? So this becomes a message passing neural network essentially, and this is the graph neural operators, as people call. I think this came also in the same paper as the Fourier neural operators. I'm not sure. But once you can think of doing these things in the Fourier space, you could also think that if you take the graph Laplacian and consider its eigenvectors or eigendecomposition, that also gives you the graph Fourier space. And so the Fourier neural operators can also be extended to work on graphs. So okay, since graph neural operators, now you can define this. That means that you could actually solve these over graphs. Okay, and that of course graph structures are more general than discrete grid structures, and therefore people there's a good chunk of work that would actually operate on graphs and this discretize spaces as graphs and then operate on these graphs one way or the other. You can think of a graph transformer, or you can think of graph message passing, so on and so forth, to yield the solution. Okay, and of course you can coarsen these graphs, and then you can form these into coarse to fine architectures in order to define the solution gradually as you go. Okay, so you can engineer this as much as you want to come up with more efficient architectures, and essentially there is no ending to this. Right? So we ask a little different of a question. Rather than trying to engineer these pipelines, okay, assume that you are given these arbitrary domains. These are completely, really, really arbitrary in the sense that they cannot be approximated by graphs because sometimes they have these cell structures, sometimes they have these edge structures, right? Sometimes they are point clouds and so on. And the name of the game is how would you solve your PDs over these domains? That's fine, right? It's fine to ask. And the question is, does it happen in real life? Well, actually, yes, in a lot of the cases, and I will explain. So, for example, if you want to solve PDs on molecules, right, and study them, or over CAD models, these are completely discrete structures with not so graph-like connections. For example, there could be some higher order connections like atomic rings, right, and functional groups, which might carry some information, not just on the edges, but on how these individual atoms come together and form a higher order bond. Or in CAD models, where you have vertices, well, edges, but also loops, right? And these carry meaning in themselves. And these are not really edges of a graph. Okay. So people use boundary representations to talk. Right. So this is the first thing, right? The first thing is the domain. And again, this domain gets arbitrarily complex once you start to study different things. Like, for example, if you generalize your graph structures to incorporate other types of entities, such as simple triangles or polygons in the data structure that you are defining, then that means perhaps you could talk about more complex structures in this case of life, right? Here's a combinatorial complex is one data structure which can contain arbitrary higher order information is significantly richer than a much limited complex, right? And these are all examples, of course. But so this is the first thing. First thing is the domain, okay? That you want to be solving PDEs on arbitrary domains. But second, and more important, I think, and this is the main motivation of our work, is that certain PDEs naturally define quantities on non-graph-like entities. For example, if you have some kind of so here's a Maxwell's equation. I'm not going to get into the symbols, but you can think of the potentials or pressure, things like this, as living on vertices, okay? So if you want to solve for a potential field or pressure field, it might be perhaps okay to leave everything on the nodes. Or if you are solving for electric field, you have to consider edges, but graph would already have them. So that means you are using graph neural operators and you can solve for them. But certain other quantities like fluxes, okay, the magnetic field and so on, they are of two forms. Or densities and charges, they live in three forms, which means they are, for example, electric field would live on phases and the densities would live on volumes, okay? So these are really the surface elements that, when you discretize your object underlying continuous space, you have these are defined naturally on these quantities and not on vertices or edges. So these other discretizations that one might do would actually throw us out of a plausible physical solution, right? Because this is not where physics is defined. You have to solve the PDE where physics is defined, okay? And that's the other aim. So we want to be operating on arbitrary domains, and we want to solve the PDEs or actually treat the physics in where they are defined. Okay, and if you collapse these things just to nodes, right, we are going to lose maybe some conservation laws of physics. Maybe we are going to lose coupling across these dimensions. So you are not going to be able to flow from edges to the faces and so on. And we are going to, let's say, certain effects, right? Maybe some kind of I don't know, turbulence-like effects or more interesting dynamical effects that would not be happening, right? That would need cycles and stuff. Perhaps they would not be happening. So actually, the underlying character of the solution is going to be different as well. So we may not capture this very well. Okay, so this is the goal. We are going to take these topological domains, and we are going to think of the domain to be separated than the signals that are defined on this domain, okay? So we are going to, think of the chains, for topologically inclined people, 0 chain, 1 chain, but we will also think of the cochains separately that are, defined, that are features attached to these chains. And then we are going to design these operators as well. There will be certain inductive biases in these operators, of course, and I'm going to touch a little bit on how we can develop these things that are going to operate across different dimensions, but also they are going to interact these dimensions. So in the end, we will obtain the PDE solution. Well, so there will be a field predicted over the entirety of the topological domain that we choose. Okay. So in this work, we are going to choose our topological domains as cell complexes, which is going to be a generalization of, graphs and meshes and many of point clouds and many of these structures, but also it can be slightly more general than that. Okay. So just to, as a reminder to people who may not otherwise know these, a simplicial complex is the simplest form of complex, let's say, we can think of that goes beyond graphs, can be thought as relations of sets. So let's say we have these nodes, 1, 2, 3, 4, okay? And then we are defining edges between these nodes, 1, 2, 2, 4, 3, 4. So this entire graph can be thought of as a subset of the power set that can be generated from the set of vertices. So I take the elements 1, 2, 3, 4, think of the power set that I can generate from these, and the subset of this power set dictates the relationships, and that simplicial complex is exactly that, right? So we can write everything in terms of sets. Now, if I have a triangle, right, a higher order connection, and if I don't want to chop this triangle up into individual edge pieces, okay, so but treat it as an individual entity, I could actually add the set 1, 2, 3, right? So the cardinality of that would be 3, and this set would still be a valid simplicial complex. Okay. Just like we assign orientation to the edges in a graph, so like a directed graph, we could also assign orientations to the triangles, right? So some computer graphics people would actually know it by computing the surface normal by using a right-hand rule and so on, right? So it depends on how you orient your right-hand rule, you are assigning a different orientation. But because the triangles you see here are oriented, I am going to use these parentheses instead of the brackets. Okay. So a simplicial complex is essentially built by integrating all these pieces together. So you can have edges, you can have triangles, you can have vertices and so on, right? As much just like in the relationships that I have been showing. Now, of course, when you have a graph, and sorry for this little error, when you have a graph, you could actually think of going from one vertex to the other, right? And in this case, if it's just a graph, you can traverse from 1 to 2 and then 2 to 4, okay, over edges. So edges are one-dimensional objects, so this chain is called a one chain. Similarly, though, you could walk on the triangles, okay? And that you would say, well, I'm first going to touch this triangle and then this triangle, okay? So you can write this as a chain over the triangles, and actually, you can write it as a linear combination of these two triangles and say that the resulting object lives in the space of two chains. So naturally, when working with these objects, we want to retrieve as much information as possible from the graph domain, because there are certain things that are very well studied, and not only in mathematics, but also in machine learning, in the sense that we know how to do convolutions on graphs, message passing on graphs. So can we leverage some of these ideas also for these guys, right? So in the end, I'm going to design a message passing algorithm for not simplicial complexes, but cell complexes. But it's also important to treat the simplicial complex. Well, see how we can construct certain things on a basic object like simplicial complex. Okay, so let's look at this. Let's look at this and see that there is some kind of a graph that I'm showing here, 0, 1, 2, 3, 4. Okay, and the boundary matrix B, okay, or the incidence matrix, as they call, would relate vertices to edges, okay? Vertices to edges, which means if you want to go from 0 to 1, right, you know that 0 is a vertex of 0, 1, and you are going out of 0, so this is going to be a -1, okay? You can do this for all the edges and get some kind of a boundary matrix. And if you just multiply B1 with B1 transpose, okay, so that would be like a, vertices, number of vertices times number of edges times number of edges times number of vertices operation. So that will be number of edges by number of edges, sorry, number of vertices by number of vertices in the end. And this would give you a Laplacian. In fact, the classical Laplacian, the graph Laplacian that you can think of. Okay. So now consider that you have this object here, which is the same graph, but now I included the triangles. Okay. So you can similarly write another boundary matrix, which would relate the edges to the triangles now. So if an edge is a part of a triangle, then you would, and the orientation matches, you write one. And then if you traverse the triangle in some kind of an order, you can put a -1 if you are going against the order. Okay, so you can write up this number of edges by number of triangles boundary matrix as well. So this would be a two-dimensional, right? So because the triangles are two-dimensional objects in this case, so you're going to say 2. Okay, so now I can think of another object, which is K, which is the rank or the dimension that I'm talking about. So 1 or 2 here. And you can say that, well, B1 transpose this time, okay? So number of edges by number of vertices times B itself, B1, is going to give me something like number of edges, but number of edges. But equivalently, I could also take B2 and just compute B2 times B2 transpose, which also gives me number of edges and number of edges thing, right? And these are both valid Laplacians, actually. But if we add them up, this object is called a Hodge Laplacian, and it's kind of like a canonical Laplacian that you would construct for these spaces. Okay, so many of the things, operations we can write in terms of the Hodge Laplacian, or other derivatives of these Laplacians that one might think of. For example, you can think of a normalization of this, right? Because usually in graphs, you always work with a normalized Laplacian. So the spectrum is bounded and the probability is preserved and so on and so forth. But here, it's going to be a little harder. So we actually wrote a little paper on how to normalize this. And you can get some interesting Laplacian normalizations if you become a little careful about how you define your random walk and how you define the resulting Laplacian. Okay, so I'm not going to go into this, but I'm just saying that designing Laplacians for topological deep learning operations is a form of art, and there is good research going into it as I speak, I think. Right. So graphs are these objects where vertices are tied to edges, right? So on the boundary of the edges. Hypergraphs, on the other hand, are those very abstract structures where you lose completely the relationship between, what is kind of like what is contained in what, right? So an edge is not very different than, a pile of vertices and edges together, right? So you can imagine that certain vertices are assigned to hyperedges and losing some kind of the underlying rank, essentially. Cell complexes preserve this, and therefore you have these two types of boundary relationships between two cells and one cells are zero cells, which are vertices. Okay. So you can think of the cell complex as a simplicial complex, but with arbitrary polygons instead of triangles also. Okay. We also defined this, kind of a unifying complex, which is a combinatorial complex where you can define basically points, graphs, simplicial cell complexes, but also hypergraphs as special cases of this object. Okay, so if you design a neural network that can operate on this structure, you can deal with a lot of things. Okay, so the combinatorial complex is this triplet, okay, S, X, and rank, where S are just the vertices that you are provided with, and X are the relationships that you want to choose. So you can choose, arbitrary relationships. You can choose them pairwise, but you could also choose higher dimensional relationships or higher cardinality sets similarly, right? And X essentially, as I said, is a subset of the power set generated from S. And there exists a rank function, okay, within this combinatorial complex, where if two subsets of this relationship set X are included in one another, then the rank of the smaller set should be smaller than the rank of the larger set, basically. Okay, that's what the second condition tells you. So elements of X are called relations, okay, and the elements of S are called entities, usually. But we are not distinguishing a lot between what a relationship is and what an entity is. In fact, all higher order entities, right, are kind of relations. So you can see it here. So S0, S2, S1, these are vertices. They are connected either by an edge, which is a purple thing, or by a triangle here, which is a blue thing. But it's not restricted to this. You can choose these arbitrarily, right, as you see in this one. Or you can choose, this to be of rank 2, blue, and then another thing that includes blue, which is green, and that's going to be a higher order cell. Okay. So once this is done, you can think of your neighborhoods, right? And here, if you have a set and the anchor point is the red point, you can think of all the points that are around it. That would be a vertex neighborhood, right? So if you take an epsilon ball and consider all the points which are falling into this ball, is a vertex neighborhood. But sometimes you are presented a graph, right? So if you think of all the points that are in 2-hop, for example, right? Your neighborhood is populated not just by points, but also by edges, right? So you have neighboring edges and neighboring points. And neighboring edges are form your one neighborhood, and neighboring points would form your zero neighborhood. Now, if you go here, then you see that in the vicinity, there are some faces or polygons in this case. And that means you are neighboring some 2-rank objects, right? So you can think of the collection of all these things. So your neighborhood is rank dependent or dimension dependent. And then if you take any subset of this given some kind of a combinatorial complex, okay, then, so basically, if you just take a local neighborhood out of your combinatorial complex, then it's going to be a combinatorial complex itself. So the CCs are closed under neighborhood taking, okay, that you can say. Okay. So now you can define, if you know all of this, and if you just observe what a graph convolution is, right? Adjacency matrix on the left, features in the middle, and then weights on the right, and some activation function, which is the graph convolutional network. You could define a topological network by just replacing the adjacency with a rank-dependent adjacency. Okay. In this case, I minus perhaps a Laplacian. So this is the most basic topological convolution that you can write, but of course there are many other things you can do. For example, this would be one, right? I'm not going to get into the details, but because your dimension grows, you have more flexibility in designing what a convolution or a message passing would look like. And also people started from these convolutions in the graph domain, but quickly transitioned into message passing because, well, these spectral convolutions and stuff didn't yield a lot of efficient algorithms, but message passing did. So we are going to do the same, and we are going to think of a higher order message passing. Okay. As I said, so if you want to pass, locally think of the message passing around the node, you have 3 kinds of neighborhoods: vertices, edges, and faces, right? And then there are messages between vertices to that vertex, from faces to this vertex, and from edges to this vertex. So you have 3 kinds of messages coming in. Now you could aggregate these messages within each neighborhood, within each dimension, essentially. And then you can send another message from each of these dimensions that you are considering to the current dimension, which is 0, because I'm interested in a point right now. But it doesn't have to be. Okay? So this is your message passing operation. So it's kind of like a hierarchical message passing, if you want. You pass messages within each rank-dependent neighborhood, and then the result is propagated or transmitted once more to the central element. Okay, so you can stack these message passing, operations, and then you can create these deep topological networks that can operate, let's say, on cell complexes, on combinatorial complexes. So from vertices, for example, zero cells, you can pass a message to the two cells, right? You can pass a message from a vertex to a triangle if you want the triangle to be informed by what vertex has to say, right? For example, if you want to, I don't know, dissipate heat over a surface, perhaps you don't want to dissipate it over vertices, but you actually want the heat to transmit from a vertex to the interior of a triangle and then to the edge, and from that edge to the other triangle again, right? So this kind of a dimension mixing evolution flow is actually possible if you design your algorithm carefully. And of course, you see, kind of where this goes, right? Interacting ranks become really, really important if you want to design physically meaningful architectures, essentially. Okay, so I'm not going to go into this, but topological deep learning usually tries to, make it easy for you to design an architecture on topological domains. So given a vertex set S, you define your complex in any way you want, right? And this is an art form. And then you define how you would be taking neighborhoods on this. Once you do these things, which are, application dependent sometimes, we provide all the operations and the toolkits so that you create these deep architectures on them. Right? So we provide some libraries on this and so on. So the idea is that you are presented some relational data, and instead of trying to chop it up to graph, for example, you take this three-way relationship ABC. If you want to treat your native data as a graph, then you are going to break this relationship into AB, AC, and BC and abstract it away with a graph. This is fine, but this type of three different objects or edges is not what this ABC cell is about, saying something else, okay? So we instead want to kind of develop these statistical models that can digest this relational object in its most native form. Cool. So now this, knowing this and knowing how these structures look like and how we do message passing and convolution on this, we could actually come to the neural operator part a bit. So as I said, the primary motivation is that there are certain physical quantities, again, application dependent, but happens overall in many applications, is that the temperature, pressure, potential can take zero forms and define on vertices, but the electric field and circulation and line flow, Darcy flux, these are one forms. So these are defined on edges, so cochains. And quantities like magnetic flux, they require a support of a phase, right? And then charge, mass, source density, these are volumes. Okay. And please, when you think of cell complexes, think in general, right? Although we speak of discrete forms, right? In topology, there are many homeomorphisms that are going to yield the same object. So all these things that you see here can be cell complexes. Okay, so what we are doing is quite general, and it's going to work on many, many domains that we are all used to. Okay, so this correspondence for people who are more curious is known as the Durham convention or the Durham correspondence, and this is one of the I think most beautiful thesis of discrete exterior calculus. Okay, which I can only get into the details so far, but essentially we are going to learn to do calculus on these abstract, well, a little abstract, discrete domains. Okay, so it's a generalization of calculus to this. So we are going to basically define differentiation and integration on these, arbitrary k-dimensional k forms. Okay, So here's, some oriented K cells, okay? And then you make up this chain, right? As I said in the beginning, these chains can be edges and you walk over a path, but these chains can also be um, over triangles and anything, right? And once this is your chain is defined, you are also going to speak of your cochain, which are the signals defined on this chain. Okay? And once you also do that, then this operation is going to be, well, or DEC is going to give you a discrete integral, which looks like this. And that is going to be the analog of really integrating over a k-dimensional region. And as I said, looking back, phrasing it more from the discrete exterior calculus, you have boundary matrices, these D0, okay, and D1. As I said, these relate edges to vertices and then triangles to edges and so on, right? And you can define them. And we are going to work with these objects. So the premise is that the boundary of a boundary is going to be 0. Okay, that's a big premise. That's a big topological constraint that we can operate on, and many things fall from this. Okay, it helps us to conserve quantities and to yield meaningful structures and meaningful message passing operations, essentially. Now, of course, we are going to talk about passing information from faces to, for example, to the edge, right? And that's also going to be given by this kind of an operation where your M is kind of a horse star, okay? So you can go from edges to faces, but also from faces to edges in this way. And as we have seen, your Laplacian is going to be very helpful in doing so, right? Because you could either write it between faces, so a Laplacian by considering the boundary between edges and triangles, or between vertices and edges, and they are kind of relatable, but one is coming from down, the other is coming from up, okay? And these yield in this, so you take this edge, and then you operate D1, and then you go to these faces, and then you take these faces with delta 2, you go to this edge or these edges, essentially. So this is the components that make up the up Laplacian. Okay, so which is some kind of a connection, well, between the neighboring edges. But here you could go from this edge to vertices, okay, and then from these vertices again to this to the edges, right? So this time it's delta 1 and then D0. And that's going to be your down. So these are the primary operations that we leverage. And then the algebra is defined over these operations. And there's a lot of theorems that help us develop meaningful operations. Okay. Given this, now I can define a topological neural operator. It is going to be a map. Okay, and that map is, of course, going to be a neural network between, well, this product space, okay, this object X, right? And that's K is a finite cell complex, right? So and this is going to be a function defined, and Y in the same way, okay? And that neural network is going to be approximating a target operator G from chi K to YK, or XK to YK. Good. Now, there are certain good properties that we want this to satisfy, and it satisfies. One of this is there is a cellular intrinsicness. So you should think of the same intrinsicness as the smooth manifolds, okay? But everything, this topological neural operator is built from cellular operators, okay? So it depends on instance structure and metric structure, but it's not dependent on some kind of a fixed grid or ordering, okay? So we are not further discretizing this space or anything. So given the cells, that's intrinsic. And the good part about leveraging such operators, as I said before. Well, this boundary, co-differential, okay. These are, well, so there's an output at 1 degree, which depends on the inputs at another degree, right? So you are interacting the vertices and the edges, essentially, or edges and faces. It's very important. Okay. And the weights are going to be shared across discretizations. So there is some kind of a consistency constraint that is implied. Okay. So if I take an operator and then, kind of, well, so if I essentially lift a structure, so lifting is deriving the higher order analog of that structure and then restrict it back, I should be getting the same neural operator as if, I was working on the lifted space and then restricted. Good. So the general TNO layer can be written as you see here. So it uses these, boundary matrices and the Laplacians and so on. Okay. And W's are learned. Now, what this helps us is to take a PDE, okay? For example, let's take Maxwell system. It's a coupled system. It's a coupled, so there's electric field, magnetic field, and as I said, electric field is defined on the edges, magnetic field is defined on the faces, and so on. Okay, so it's a coupled system of differential equations. And now we want to realize this as a topological neural operator, which means you want to have a corresponding architecture that can solve this PDE. So what you do is you really only look into the dimensions of this coupling. And this helps you to, well, this basically induces a topological neural architecture, okay? Which so you have your input, and then you want to have your output signals, and this is the H1 is on the edges, H2 is on the faces, okay? And then you know how the information is going to be communicated directly, right? And so you know how your learned operator can look like, which is great because purely observing the structure of your PDE essentially gives you a way to design a neural net. So, well, in the general form, of course, we have an encoder and then multiple layers, and then we have a decoder, okay? Perhaps a UNet even. But these can also be identities, okay? The decoder and encoder can be identities, and you just have the topological layers, completely fine. A linear realization is stated here. Well, of course, this is only, it's the most basic thing you can do. In practice, what we do is a hierarchical realization of this. And so that means that we take our space, the discrete space, and coarsen it further, okay? And the neural operator is operating on the coarse level. That is interesting because the coarsened objects, if you combine it with the initial object, can also form a cell complex in themselves or a combinatorial complex in general, because already cell complexes are hierarchical structures. So you could do that. One perspective. The equivalent perspective is that you do a coarse to fine neural operator. These are equivalent. Where you solve your neural operator on the coarse level and then come back to the finer level and then refine it a little bit and again. This has an exact equivalence also to a two-grid V cycle or a V cycle in general. Okay, so there are the restriction maps and then there is the refinement and so on. Yeah, so for example, you see here some kind of a implementation of this hierarchical idea by using a De-Leonine triangulation on an input field. And then you cluster these De-Leonine cells, and then these become your higher order cells or coarse structures. And then through KNN, you find your coarse. It should be the same as applying this neural operator and then, yeah, so, and then restricting it to this one. Okay. Yeah. So instead of going all the way here, right, you kind of go to the core structure and do something there. Well, that propagates a little more information. You can see it as a receptive field as well, one way or the other. There are multiple connections, which I'm not. Typical Fourier neural operators as a special case of this. Okay. Um, if you consider the discrete Fourier transform, of course. So you take your, well, HNO or TNO, HTNO or TNO, and then you inject this Fourier transform, and then you can actually realize this is a linear FNO. You could also, of course, obtain GNOs as special cases. Okay, from the kernel perspective again, what I was mentioning in the beginning. But if you do a rank 0 topological neural operator, okay, that's going to be, well, with some incidence that is supported on edges, then you are going to obtain the graph neural operator. So we provide the proofs of this paper. But because it's very general, then we can take essentially many PDs that you know, and in the paper we have much more, and look at its core discrete exterior calculus structure. So which is basically which kind of a PD, which kind of a, well, you first look at the underlying continuous PDE, okay? And then you think of the discrete exterior calculus operations, and you see that, you know, there is a certain form of DEC that this realizes. And then just by looking at this, like for example here, you can immediately see what kind of an operator, TNO operator, that it induces. Okay. So you can do this, and we do this for many PDs. And therefore it poses a very nice generalization. And of course, it propagates information in the correct rank. So here the purple is the orange is the rank 0, purple is rank 1, and 2 is rank 2. Okay. So you see that many PDs are defined across different ranks, and you need to respect that structure throughout learning. Yes, and we have seen this before. So. There is also a nice, I'm not going to go into this a lot, but this kind of a, you know, perspective gives rise to this Hodge decomposition, where once you have a flow over this complex, you could actually decompose it to the exact harmonic and co-exact components. So it's, you know, divergence curve and harmonics and so on. And that gives you an interpretation of the underlying field. You could either use this to design your own neural architectures, right? Because you can now process, you know, maybe divergence differently than curl and so on. Or you could later, once you learn your field, go back and look what kind of a rotational components or what kind of, you know, inward outward flux that this is inducing. Okay, so there's an added layer of interpretation when it comes to TNOs on top of these other. Okay, so we evaluate on a bunch of things. Well, I don't have a lot of time, but I'll briefly talk about them. So we first take these simple data sets. Okay, so most of the time what you do is you take some PDE and you simulate, and then we use some data, simulated PDE data, and learn our neural operators on this, and then try to predict the outcome. So we do this, we experimented with different discretizations of this, of course, right? So what if the underlying domain doesn't correspond exactly? So there is certain robustness to this. And also, what if you don't see the exact same topology? We also tried this, and we are doing more experiments on that as well. But essentially, if you take all these other neural operators, okay, in simple baselines, you can see that there is a little bit of an advantage. And we didn't even engineer things here, right? It's just the out-of-the-box TNOs, which I presented. And then you can take these, well, there are some other data sets, especially ME-Wing is interesting because it's kind of a large scale, you know, data set where there is this wind on the wings and, you know, or other dynamics on the wings. And here you can see that transsolver baseline is included, and we do a little better. So, all these things are actually helpful in practice. And you could actually visualize, of course, you see that there are interesting geometries here, and there is a source F, okay, here, and a target U, and you want to reach that. So you can do this with MPNN. So with a message passing neural network, that would be the simplest baseline, right? Or you can do it with Rigno or whatever, and then you can record the error of the MPNN and of the TNO, right? And you see that there's a decent improvement. And these PDEs are particularly important because they are actually defined. So the signals are actually defined on the cells, so two cells, and not on the vertices. Yeah, so some comparisons with Rigno are possible. So this is the elasticity and the airfoil. Okay, so you have some kind of a ground truth, and it's what we obtain. That's what Rigno obtains. So you get a little better result in general. Sometimes maybe not visible, so visible across, but yeah. So usually if you look at the error heat map, it's a bit better identified. Okay. And the hierarchical version, of course, performs usually much better than the TNO itself. Right. So I just wanted to give you a super brief overview in what we do in TDL beyond neural operators. It will just take maybe 5 minutes. So we try to generate these higher order complexes, so these cell complexes and combinatorial complexes, but also generate graphs, which works really well. So this is a work called HOGDIF. And we have comprehensively evaluated on a lot of benchmarks, and see that there is a benefit from including higher order information as a guide to perform molecule generation, even if it's graphs. And we do create these higher order molecular languages or grammars that take into account these functional groups or motifs in the molecule into a string representation. And we use this string representation in developing foundation models, or first of all, generative models, of course, right? Because you can just use these embedded strings and pass them through some typical, grammar encoder or decoder, and then do a latent space diffusion to have generative models, which work also extremely well. So this work is under submission right now. And you could also do a foundation model on these interesting string representations to outperform, all the things basically that exist on some molecular benchmarks. So these are, quite good. We also think of the sheaf formulations of these message passing operations, and we also think of the sheaf formulations of topological neural operators. And this is a very general formulation, which says that you can take many of the neural networks, and write them in the language of sheaves, and that's completely fine. And some people do cosmology with deep learning, which I don't know, but could be interesting to you. And we do look into some multimodal AI because cell complexes become these, or combinatorial complexes, unifying structures where you could actually combine a lot of the modalities into one modality and then natively perform convolutions on these merged modalities. That's totally possible, and we have explored this. And we are trying to release all these things under TopoX. Not up to date all the time, but we are slowly trying to bring it to the level that we want. But you can go ahead and play with many things even today. And we released the survey on opposition paper essentially on what you could do in your free time if you are really bored. Yeah, so I have to thank all these people too that realized this dream a little bit. Right. Yeah, and we are going to do a lot more on topology and deep learning. So more works are coming out, and more works will be done hopefully. Okay, so that's it. Thanks.
Thank you, Prof. Thank you very much, Professor Tolga. Guys, if you have any questions, please just unmute yourself. In the meantime, there's one from my end. Prof, of course, the paper is highly technical, but when you look at, according to the discussion about topological neural operators, somewhere I said they sort of operate in sort of the value cochain sort of field. And at a technical level, that's what I got. Like, if you look at concepts like maybe potential to flux, um, you see that they bring some power within deep learning. But also, we know the classical neural operators, uh, for example, in areas like graph neural networks, they sort of propagate through node to node. And my question is, when you look at the computational resources that might be needed, when you look at the topological neural operators and the classical neural operators, topological neural operators like sort of computationally cheaper or they're expensive? That difference, yes.
Okay. Mhm. There's a good point, but how much expensive exactly? Because usually, um, I mean, that's a common question about using higher order information because your worst case computational complexity grows with the dimension, well, exponentially, or like at least, even polynomially is very dangerous, right? Um,
Yes.
so, but nature is very sparse in these connections. So let's put it this way. There are many, many, let's say 10 billion people on Earth, right? And they all form families, let's say. They are all some part of a family. How many families are there? Not a lot, right? Not
Yeah.
not combinatorially more, surprisingly, right? Or how many, like if you think about it, like in a mesh, right? In a mesh, you have vertices and edges. How many? The edges are not a lot more than vertices, or triangles are not more than edges. Not really. So this complexity doesn't grow in the worst case in practice. Okay, so
Okay.
yes, they are slower, of course, but mostly because they are also taking into account these, higher order things. So there is an added complexity, but we analyze the computational complexity, of course. Um, Average case, I should say, is not that bad, and real life data is even behaving better than the average case in terms of providing amount like certain higher order interactions.
Okay. Well, thank you very much.
If I understand the question correctly, right?
Sure, sure. Um, I haven't seen any other question. The other one is about the concept where you talked about. I think I would call it some sort of transformation where topological structures collapse when we move to graphs, like graphs collapsing to nodes, and like
Yeah, I mean, you either collapse to nodes or to the edges, right?
out to the edges, yes.
Yeah.
And the like, do we lose some information when in terms of comparing the topological neural operators and
Mhm.
graph-based like sort of neural operators? So by the time we move to nodes, are we losing some details within maybe the structures?
Um, so what you are losing first is, so all these physical processes, I mean, it's physics. So there is so when you say heat is not defined to physicists, is not defined as this, or solving a heat equation. Solving a
Yes.
heat equation, if you discretize and if you do not conserve the quantity itself, right? So there is a conservation law associated to calling it heat. They don't call it heat because of the equation. They call it heat because your diffusion respects the conservation law. So now, the moment you do this, you are going to sacrifice these conservation laws because your discretization is not respecting it anymore, right?
Yes.
So this is one thing you lose. Another thing is, of course, you lose the interpretability in the sense that if your magnetic field is defined on, physically defined on a face, but your output cannot give you the output on the face. So
Sure.
how can you call this a magnetic flux now? So all these graph, let's say graph versions and stuff, if you take its output, and if you want to call it a magnetic flux, then you need to detect these cycles in the graph or phases in the graph, and then you kind of average the, whatever edges you have around. I don't know what you do, but you do need to do something, right? To really call it a magnetic flux. So
Sure.
so you lose this sense of physics essentially, right? And let alone that you cannot truly process the underlying domain. I think that's this is what you lose.
Uh, Thank you, Prof. Now that intrigues me a bit because I, if we stay within a lower dimension like 2D, let's look at images.
Mhm.
Um, where we know that these neural operators have given us some sort of state of the art models. If I bring in topological neural operators, would that be an overkill? Yeah,
For what exactly?
like if we just think about images in 2D,
It's just
because
imaging.
yes, would the power that the neural operators, the topological neural operators are bringing, would that be an overkill?
Could be.
Okay.
Could be because for images you have very nicely engineered architectures, right? For example, there is a natural transformer.
Yes.
So the graph transformer, a mesh transformer, these are partially excellent, right? These are
Yeah.
not demonstrated. Like there are so many versions of graph transformers, I don't even know which one to use. But for images, there is one transformer that, works perfectly. And like,
Yes.
for example, Swin would be very hard to beat, right?
Yes.
Um, so yes, that might be. But if you are considering that you have an underlying mesh, usually like in computational fluid dynamics or all these CFD people, what they do, or like finite elements people, they have an underlying, even if it's 2D, a mesh. And that mesh can be topologically interesting with holes and stuff, which is not like an image, right? So you don't know what to do around the boundary and so on. In
Yes.
these cases, I think it can be helpful.
Perfect.
Yeah.
Thank you. Thank you very much, Professor Tolga. This has been an interesting discussion. And one takeaway for me is I think the more you're exploring physical sort of quantities or entities, I think topological neural operators have a big role to play and can give impressive results.
Yes,
Um,
also a way to study these things, right?
yeah,
Not just like you can always approximate things, right?
yeah,
But if you
yes,
want to perhaps truly study what happens to these PDEs, right? If you don't want to do an analysis of the PDE and stuff, perhaps framing it in this way might be a little better.
okay. There is a question in the chat, Prof. I don't know whether I should read it or you will read
Right.
it yourself.
So when we
Okay.
apply higher order approaches with the topological spaces on an unstructured data space, say a uniformly sampled censoring voluminous data space, how do we construct the so-called combinatorial complex? How do we know the lifting functions among the rank doesn't introduce biases? Yeah, it's a very good question, I think. Um, well, unless there is a physical meaning into the complex that you are constructing, then you don't know. Um, so there are a couple of, let's say, ways to go about this. First, there are ways to learn this. So you can learn the lifting functions from data as well. Of course, nobody combined it with these neural operators. We also didn't do it, but maybe this is very interesting to do. So kind of you can learn your discretization while solving your neural ODE, I guess, perhaps. I don't know. Second is which is interesting. So I did some experiments in some domains where there was a physically meaningful lifting. For example, let me give you this example from which is really intriguing to me. So from this, I didn't talk about it, but quantum error correcting codes, they have a natural lifting. Okay, so they are apparently a simplicial complex, and then they have a natural lifting. Now, we did some experiments where we used the nature, and I was so happy to see this because the natural lifting would really shine right in this TDL approaches. And then we made a comparison. So I was randomly lifting certain, cells or certain structures to cells, and then processing them versus using the physically meaningful lifting. Now, the random one was outperforming the physical one. So that made me question a lot the meaning of lifting. Simply because something is physically meaningful doesn't mean that it's going to be computationally better. Right? So, as if it's just like you could always create mathematical structures that are more convenient than what physics dictates. So it might be very interesting to think about not just physically meaningful liftings, but what liftings would actually help learning. I think that's a better question to ask, right? And maybe learning to lift is one answer, but the other would be to really think about the underlying computation together with the physics. So maybe there's a sweet spot between computation and physics where your lifting lies, or the ideal lifting lies.
Thank you, Prof. I hope Ming has been answered very well. Okay, this is Anne Farm. Thank you very much, Prof.
So much.
If there are no further questions, I really want to thank everyone who has tuned in today, but also thank in a special way Professor Tolga for saving up your time and really
Thank you so
decided
much.
to talk to us. Thank you very much.
Bye bye.
Bye bye. Bye bye, Prof. Bye bye to everyone. And see you guys in our subsequent sessions probably next week.